Hello and welcome to the UFS webinar. This webinar is hosted by the National Weather Service, Office of Science and Technology Integration. The goal of this webinar series is to enhance communication and share advancements in all aspects of the UFS in both research and operational settings. I am Karen Keith and I am here to help coordinate and deliver the webinar. Feel free to contact us at OSTI if you have any comments or suggestions. Also, if you have any recommendations for speakers that you would like to present to this webinar, your recommendations to ufs.modeling@noaa.gov, and we will take your suggestions into consideration. Due to the high number of attendees, you will be in listen-only mode during the event. You will not be able to unmute. If you have any questions now or during the event, please submit them on the Google document that I will provide in the chat in just a few moments. The presentation lasts about 45 minutes, followed by questions and answers for 15 minutes. Please type your questions in the Google document throughout the presentation. Today's presentation will be climbing down Charney's ladder. Before we get started, I want to quickly show you how to sign up for the webinar notifications and how to view archived information. Here is the UFS portal, ufscommunity.org. If you scroll down to the bottom to the events section, you will be able to register for upcoming webinars and recommend a speaker. Also, if you click on the UFS webinar series, you'll have archived events, and so you can look at the recordings from previous webinars. Okay, so today's speaker is V. Balaji, and he'll be introduced by Ricky Rude.
Thank you, Karen. It's my pleasure to introduce Balaji. He's at Princeton University's Cooperative Institute on Modeling and Earth Systems, and an associate of the Princeton Institute for Computational Science and Engineering. He was for many years head at NOAA GFDL's Modeling Systems Division from 2003 to 2021. And he was also among the first recipients of the French President Macron's Make Our Planet Great Again award. And he has been spending his time between the US and Paris for the last few years. Balaji is one of the best strategists that I know for thinking about computing, modeling. His background is in physics. And his experience at GFDL has been very integral to the success of the modeling activities at GFDL. So with that, I would like to introduce Balaji.
Thank you, Ricky. Thanks everybody for coming. So I will be giving this talk as to introduce. I'm going to be talking a lot about the history of the models that we've been building. GFDL is very, very much part of the history, as you'll see. And we'll talk about what is happening in computing that requires us to think about changing tack a little bit, because the nature of computing technology is changing. And I'll be speaking about it in the context of the work that GFDL has been part of from the beginning, which is within the scope of UFS, but it's going to be more focused on the climate side of things, long-term, the studies of long-term changes to the climate. And I will kind of give a brief, and I'll try to introduce the problem and how it started, and then go through the history of it. So we'll talk about climate science and climate models, and I'll contrast a little bit about what weather and climate, what the difference is. And I'll talk about something that the inventor of the computer, John von Neumann, who also worked in Princeton and actually was responsible for the creation of GFDL, he called it the infinite forecast. So we'll talk about that. And then I'll get into how models have changed from the time of Charney to today. The end of Dennard scaling, which is the inflection point in the history of computing that we are currently going through. We'll talk about why many people nowadays talk about machine learning and so-called artificial intelligence, because the modern computers are very good at that. They're much better at that than solving equations, which is what we have been very good at doing. So if you're going to be doing learning, I'll talk about what learning means in the context of climate modeling, and then I'll get back to the theme, which is climbing down Charney's ladder. I'll explain what that means. Jules Charney is one of the pioneers and founding members of our field. So let's just quickly run through what is climate. Climate is what you expect, weather is what you get, is the phrase. So weather is the trajectory of the state of the Earth system. It's what's happening from instant to instant, how it changes. It's the time trajectory of the state of the Earth system. And climate is what you expect. It means if you average over the weather, what do you expect to see? So that's what we would call the kind of long-term average of the system, or in dynamical systems terms, we would call it the attractor of the system. But the fact is that the location of the attractor is also changing because our expectations of the climate is changing. So that means that what we expect also has to change. So what NOAA does every decade is to introduce their new normal. So every decade they do 30-year averages and show them as the new normal. So then that becomes the expectation. And we have to see where we are, what the weather is relative to that. What you perceive, as you may know, is the difference between the weather and the climate. If you have a day which right now in Princeton, New Jersey today, it's around 70, 75 degrees Fahrenheit. So right now I would consider it in the spring, I would consider it a pretty warm day. But if it were July, then I would consider it a relatively cool day. So because what you do, you go into this with an expectation, and then what you perceive as a difference. The change that we are seeing, the climate change that we are seeing, is what you do. You have to remove the noise of this weather, which is the day-to-day changes, from the observations to see a small change in the signal. So on a day, the temperature can change between day and night anywhere, depending where you live, but 10 or more degrees Celsius. And when you talk about climate change, we're talking about a change of 1 or 2 degrees per century. So it's a much smaller signal we're trying to see. The residuals are very small compared to what you actually observe. What makes it even more interesting or complicated, depending on how you look at it, is that these fluctuations are on all time scales. It's not just short term. There are also very long term, decade-long fluctuations, which are also natural. They're just, even if you leave the system alone and you don't change any external boundary condition like adding CO2 to it, you will still get fluctuations. And there are systems that feed back on each other as well. And there are what would be the external terms that affect the system, which we call forcings. Human emissions of CO2 is one example. That also exists at all scales. So we are talking about a system that has time scales of minutes to millennia and microbes to megacontinents. So everything affects the climate. And so if there are, to all the students in the audience, if you haven't thought about it, the climate emergency is something you can certainly, no matter what you're interested in, any field of science or engineering is implicated. Fluid mechanics, radiative transfer, chemistry, biology, mathematics, statistics, algorithms, and so on. So please, if you have any interest in any of these fields, climate is a good area to work. So let's start very quickly with the history of climate change. So this is the Cenozoic era, the last 500 or so million years. So I hope you can see my mouse moving. Can you? Can somebody tell me if the mouse is visible?
Yes, it is.
Okay, very good. So if you go back to what the Eocene and the Paleocene, which is around 55 million years ago, you see that the temperatures, the zero line, by the way, is the global mean surface temperature of today. Relative to that, it was very, very warm. There is even the spike that goes up to 14 or 15 degrees above today, which is called the PETM, the Paleocene-Eocene thermal maximum. And then you see going down, so over millions of years, there is a steady cooling of the system. And then you get into the last million years, you get into what are called the Milankovitch cycles, these cycles of glaciation and deglaciation. The ice ages, the frontier of the ice moves back and forth from the pole towards the equator. And then you get into this last 20,000 years or so. The LGM marked here is the last glacial maximum, when the ice sheets were closest to the most recently towards the pole. So they would actually, in North America, there would be somewhere around between where Maryland is and where Jersey is today. And then you see a steady warming, and then after that you see this very unusual thing, which is for the last 10,000 years or so, we've been at what's called the Holocene optimum, which this climate is extremely stable. And if you think about it, all of the things that we call civilization today, which is settlements, agriculture, all this is possible because the climate is regular and predictable. Hominids existed even back here, but during the ice ages, but they were hunter-gatherers and they were nomadic. They basically followed the line of the ice. If the ice retreated, they moved north, and if the ice came back, they moved further south. But after this, we've been in this period where the climate is stable. We have urban settlements, we have agriculture. And if you look right at the end of the graph, you see what has been happening in the last, since the Industrial Revolution, which is the spike in temperature, which is what we are experiencing today, and that's the climate emergency. If you zoom in on it, this is a reconstructed temperature just of the last 2,000 years. You can see that there are some fluctuations. These colored lines are just different. I mean, you obviously don't have actual temperature measurements going back, so you reconstruct them using tree rings and ice cores, various indirect ways of assessing the temperature. You can see that there was this period called the medieval warm period when things were relatively warm, and then there was this cooling, which we call the Little Ice Age. These signals are not necessarily global. The Little Ice Age in particular is mostly rated in the mid latitudes. There is not much evidence saying that the tropics were much cooler than they were at other times. But then you have this late signal, which is the spike in temperature, which is after the Industrial Revolution, which now by convention we dated at 1850. And this signal is global. It is essentially warming wherever you look. So this is what we are going through. And you can see that there is the idea that there is a human influence is not just from the Industrial Revolution. You can go back. This is an article which I found, which is called The Great Dying in the Americas. So the arrival of Europeans in the Americas dates from around this time. And that led to depopulation. They basically brought with them viruses and pathogens to which the native population had no defense. And this article estimates that the death toll of the depopulation was around 56 million. And this was it was an agricultural civilization. So they had a lot of farmland. The farmland reverts to forest. And when you do that, you take CO2 out of the atmosphere. And you can actually measure that if you go and look at some ice cores in Antarctica. You can see that the CO2 level is going down. So you see that this link between, possible link between this cooling, which happens around the same time, and the CO2 going down. So there's evidence even before the Industrial Revolution that humans can affect the planet on a global scale. So why does that happen? So in 1857, Eunice Foote is often attributed to later scientists, but actually Eunice Foote is the earliest that we know today at least. So she did these experiments just using bell jars where she increased the concentration of CO2 in one bell jar and she had normal air in the other one, and she exposed it to sunlight and she found that the CO2 jar got warmer. And she did give this very precocious, prescient speculation. An atmosphere of that gas would give our Earth a high temperature. So then we go on. So this is just purely an argument based on radiation, right? So the sun's rays comes in, CO2 traps some of it. But there is far more to it than that. So then we have to go to the history of modern weather forecasting. So this is often dated to Wilhelm Bjerknes, who in Bergen in Norway, the Norwegian school is called, he wrote down what are called the primitive equations for the general circulation of the atmosphere. So it's not just that it's heating. Once you heat something, the heat can also move around. So you have to also bring in dynamics. The equations are based on Navier-Stokes equations and nonlinear, and they're hard to solve. So he could not actually come up with a way of, he could write down the equations, but he could not come up with a way of solving them. So, but he wanted to do weather forecasting, and I'm guessing it's because he's in Bergen. He's pictured here with an umbrella. I'm guessing it's gray and rainy, and he would like to know whether he should take his umbrella with him or not. And so they finally went to these empirical methods, which is based basically on having vast libraries. So meteorologists have just draw many, many maps of weather day after day after day. And they have a lot of experience. They actually know what's in them. And then you can, for anything that you can find an analog of it somewhere in the past. And then you say, okay, based on that analog, I can predict what's going to happen next. So a historian called Jacob Nebeker, he made this remark. Even though Bjerknes developed the foundations of dynamical meteorology, when he turned to actual forecasting, he used methods that are neither algorithmic nor based on the laws of physics. So it's based on just patterns. So it's pattern recognition is what we call it today, and we'll return to that in a minute. So let's quickly go through what's happening in terms of the warming and why this general circulation, why it's complicated. So because of the way the Earth's axis is tilted, most of the solar radiation it receives is in the tropics, and it's an excess of heat. So there's a heat the solar radiation is a function of latitude. So there's an excess of radiation in the tropics, and there is a deficit near the poles. So that's how the energy balance is maintained in the atmosphere. So somehow the heat must be moved from equator to pole. And when you solve those equations, when you solve Bjerknes's equations for a sphere, for the atmosphere on the sphere, you come up with the circulation which is very well known. You have these westerlies in the tropics, which are the trade winds, which are blowing west to east, and they push the air up, and the descending air creates these high pressure zones at the edges of the tropics, which is why you have deserts in those zones, because when you have air pressing down from above, it's hard to make convection. And then you have westerlies further, which is where in the mid latitudes, such as in New Jersey or in Maryland, you will find everything is coming west to east. And so the easterly trade winds, westerlies in the mid latitudes, and then these cellular circulations, such as the Hadley cell I just mentioned. So this is what the global atmospheric circulation looks like. If you do the same thing for the ocean, it becomes a little more complicated because of the continents. And this is what Wallace Broecker referred to as the ocean conveyor belt. There's more details to it that we should not take this completely exactly as it's written, but you can see basically this is what it looks like. There is an overturning circulation. It's called the meridional overturning circulation. So warm waters are moved by the circulation, trying to transport heat from the equator towards the pole. It moves warm air towards the pole, and then there is a returning flow at depth. So that's the blue curves. So this whole thing is called the conveyor belt. And you can see it's kind of complicated. It's not strictly going north to south. It also has these meanders west and east as well. And that's just because of the shape of the continents. So how do you solve those equations? So Bjerknes failed to do it with pen and paper. In 1922, Richardson tried to say that we can do this if you have a large number of people computing in parallel. So you can think of this as the first parallel computer, but you don't have computers. So he was actually doing it as people. And this is how he pictured it, that there would be somebody sitting here and shining a light, and there are people sitting over here, and when the light shines on them, they would do a calculation, and then they would pass the results to their neighbor. It's not very different from modern parallel computing, actually. So modern parallel computing amounts to that. You do a calculation for a spot, and then you share your results with the neighboring spot. So we'll get to that in a minute. Then we had this big transformation, which occurs it starts in around 1946. John von Neumann at the Institute for Advanced Study, the IAS, which is in Princeton, he invents the digital computer. So Jules Charny, by the way, one of the giants of our field, whose work I'll be returning to, he's standing here at the left. And so this picture is taken by Joe Smagrinsky, who was the first director of GFPL, actually. He's not in the picture, but he was taking the picture. So you have a digital computer. So the same thing that Richardson was trying to do in this complicated way, you can now do on a computer. But remember, these computers were actually programmed in this way. You would actually connect circuits from one place to another. So to move data around, you would have to design instead of nowadays we have programs, but before the stored program machine was invented, this is how you did computing. There were actual people doing this work. And then what von Neumann said was that you can use this new tool which he had invented, the digital computer. He said you can do numerical weather forecasting. The Bjerknes equations, which are hard to solve on pen and paper, he said you can do it on a computer. And he asked the question, so you can do weather forecasting, which is to just take the conditions at a particular time and integrate it forward, and that will give you the weather. And he asked the question, what would happen if you just kept integrating those equations forever? So eventually the initial conditions don't matter, and it will enter into some state that it wants to be in. And that's what we call today the climate. He called it the infinite forecast. GFTL so he found two centers actually, and one of them is GFTL. It became GFTL. It wasn't called GFTL initially. And you can see that its history goes back to 1956. The computer that I showed you a couple of slides ago, this one is from like 1950. So it's almost the very first computer. So GFTL goes back to the dawn of the computing era. And a lot of wonderful results which are shown on this graph. Many leading results have come out of this lab. And one important one is, of course, the first estimates of doubling the effects of CO2. So let's get to that first. So Manabe won the Nobel Prize in physics in 2021, Suki Manabe. So he and Dick Weatherall did this first calculation, the 1-day response to CO2 doubling. So in the vertical axis of the atmosphere, so you have the surface is heated by solar radiation and it loses heat to space aloft. So there is cooling aloft and there is heating at the surface. So that creates a temperature gradient. When you have a temperature gradient, it's known that the air will try to convect. It will try to move the heat. So eventually you get into this equilibrium, what he calls the asymptotic state. You get into an equilibrium between radiation and convection, which we call RCE, radiative convective equilibrium. And he computed what that temperature profile would look like. And then he kept changing the value of CO2. And the surface temperature actually keeps increasing. So this was the first 1D result saying that adding CO2 to the atmosphere, Eunice Put did it just using gases, but now he's including vertical dynamics, how the heat is transported, and he's still finding the same result. Then they went on, Kirk Bryan developed the first ocean model. Together, they developed this first couple model. You can see it's a little, very, very old graphic from the 69 paper. So I love this picture. It's almost like I think of it as a totem of the field. It's like one of the first objects from our field that everything goes back to this. But you can see that the poles have been cut off because you can have singularities. If you have a grid which is based on longitude lines, they will converge at the pole. The land and sea are highly idealized. And using these kinds of models, they try to do it now, okay, not just transporting heat vertically, but transporting heat equator to pole and all that. And they did this calculation where you're seeing now the temperature as a function of latitude. The dots are some observations. If you keep it at the standard value, you get the black line. And if you double the CO2, you get warming everywhere. So they found that. This is a 75 paper. And it did not depend on how you initialize it. So you can initialize it from above, you can initialize it from below, but it always comes to the same equilibrium. So this is the asymptotic state. This is the equilibrium response to double CO2, and we call it now ECS, the equilibrium climate sensitivity. In their model, it took about a couple of years, 700 days or so to equilibrate. In modern GCMs, it can take 1,000 years or more to equilibrate these models because we have so many processes, and the ocean in particular has many, many slow processes. So a GCM, this is what it looks like, starting from Manabe's time all the way until today. It's a grid divided around. The sphere is divided into a grid, and each grid point has a column, and you can transfer data between columns. The resolution is not enough to resolve all the processes that you are interested in. In particular, clouds you cannot resolve. They're happening on scales of a kilometer or so. It should be noted that since Manabe to CMIP6, the GFTL CMIP6 model, starting from Manabe's time, it's around a 10x increase in horizontal resolution, and also 10x in the vertical, roughly. So this is what a GCM looks like. So based on Manabe's model and Jim Hansen's model from GISS, Jules Charny, who was by then one of the leading members of our field, he was asked to write a scientific assessment, and he wrote one. And he essentially produced this result, very, very well-known result, that he believes that the equilibrium surface warming under a doubling of CO2 will be somewhere between 1.5 and 4.5 Celsius, with a probable value near 3. It's often been commented that the uncertainty bounds on this ECS has not really changed. So there's a very nice, what did Charny get so right that we have not been able to improve on it? There's some nice analysis of that. Some things are like the clouds are a very important feature as well. So we have to think about that. So you see that there were 3 runs from GFTL and 2 runs from Jim Hansen. If you look today to IPCC AR6, this is the last report that came out last year, you have these kinds of graphs. Now we are producing these. There are 114 models from 44 institutions that have led into producing a graph like this. So you're seeing that the models more or less agree on the historical change in global temperature. And these are various scenarios going into the future. So the 8.5 is the scenario where we do not do much to curb CO2 emissions. And so it continues to warm up to 4 or 5 degrees. And if you take some action about curbing emissions following the Paris Accord or the Glasgow COP and so forth, then you can probably get it down. You may be able to get it down to something where it will warm a couple of degrees and then stabilize there. So these kinds of figures are produced now using many, many models, not just Manabe's model. The models continue to add details, so they've increased in resolution. So this is this is the first, second, and third assessment reports for the IPCC, and then we start numbering, so they are 4. So you've gone from about 500 kilometers down to about 50 kilometers for the best model, maybe 25 for some models. We've also kept adding complexity. So if you look at the number of processes in each column of the model, you had essentially clouds and rain and sunshine in the early models, and now you have all kinds of other things. And computing the balance of these models is a very hard problem. The other thing we do with the model, so one problem, of course, with the Earth is that there's only one Earth and there's only one time trajectory of the Earth that we can actually observe. So if you want to ask a question, what would happen if I double CO2 and so forth, you have to do it with models. So I call them counterfactual or alternate Earths. So this is a nice study of the Indian monsoon from about 10 years ago from GFTL. So the monsoon in the Indian monsoon is observed in the 20th century to have there's a index of the strength of the monsoon, and it's observed to decline over time. And what is it due to? So you can take many forcings. I spoke about the external forcing. So the red one is what is called all forcings, when you put in all the forcings. But then you can separate it out. You can put in only aerosols. You can only put in natural forcings, which means changes in solar radiation, volcanoes, and so forth. Or you can put only changes in well-mixed greenhouse gases, which includes CO2. And you find that if you only put in CO2, you would expect the monsoon to actually increase in strength. But if you put in all of them, it decreases. So you can start now saying you can do what is called attribution. You can say that the climate change is happening and it's happening because of this or that reason. And now there is we do event attribution as well. We look at a particular event like a drought or a storm and say how much did the probability of that event increase or decrease because of CO2. Okay. Now we come to the computing part of the story. So how have we been able to do this? So the computers are basically essentially grown. If you looked on the GFTL graph, that was a logarithmic curve on the y-axis. I didn't really dwell on it, but the computing power has grown by a factor of 10 to the 10 or so. How it's happened is because of this, the technology, which is basically using etching circuits on a silicon substrate. And you can keep shrinking the size of your circuit. So a transistor, you can keep shrinking the size of it. And if you shrink it by a factor kappa, so this is the famous paper from Dennard 1974, the voltage that you need decreases, the current decreases, the delay time also decreases. So each time you shrink it, the distance electrons have to move is shorter, so the computing becomes faster. The power dissipation goes down by a factor of kappa squared. But when you divide by that by area, the power density is basically constant, which is the dissipation per unit area is constant. So without changing the power characteristics, you can make your computers faster and faster. So this has led to this dramatic 30, 40 years of growth in computing. One of the things that came out of that is what are called Beowulf clusters. So all you had to do was to put a lot of computers together, and you could do a lot of calculations also in parallel. And that lasted around 20 years. And then we started to get into the stage where Dennard scaling started to end. You can no longer shrink your transistor anymore. The current technology that's coming out now, the size of a transistor is around 5 nanometers, which is about 30 silicon atoms wide, so it's pretty small. And if you look at all these, again, this is on a logarithmic curve versus time. If you see what the microprocessor speeds, how they're changing, for about the last 10 years, there's been no change at all. The speed of actual arithmetic has stopped. It cannot get any faster. All you can do is to continue to add more and more transistors, more and more cores, so you can do more and more parallel. But you cannot actually change the speed of an arithmetic operation. And that has problems for certain kinds of algorithms, which don't necessarily parallelize as well as we would like. So the kind of calculations we do, they're called stencil operations. And stencil is like saying that to do a calculation at a particular point, you need data from your neighbors. So you call that the stencil, the shape of the neighbors that you're taking data from. So you essentially need a lot of data to do one computation. So we measure it in terms of operational intensity. How many words do you need to do one calculation? So there are some algorithms which are very, very high operational intensity, which means they can do a lot of calculations with only a few with a little bit of data from memory. Some others are much weaker at that, so they don't even get the performance that's promised. I'm not going to go into this. This is all what the US is building and what the EU and Japan are building. There are different kinds of technologies. But we can, let's say we can get to something which is called exascale, so which is the next, so every 1,000-fold increase in the volume of computing, it becomes a landmark. So we have teraflops, petaflops, and next will be exaflops. So we believe that we can get down to maybe a 1 kilometer model, which means that certain kinds of the clouds I was talking about, maybe you can resolve some kind, not all of them, but certain kinds of clouds can be resolved. In this paper, when talking, which is called "Will the Exascale Be the Rescue?" they said that in order to, if you get down to 1 kilometer, we expect to run at around 0.06 SYPD. SYPD means simulated years per day. How many years of this model you can run in one day of the time in your wall clock time. And this will be on a machine of around 200,000 nodes. I marked it here as roughly 2x Gaia, which is the machine that GFDL uses for its computing, but with new upgrades, we are getting up into this range. But you're talking about taking the entire machine. But what is really sobering is that to do certain kinds of climate experiments, I'm not talking about weather, but talking about climate, which is you're trying to look for these signals for after 10 or 100 years, you need to be able to run 1,000 or more simulated years. For seasonal forecasting, which is forecasting out 3 months, in order to test a new model, you run what is called hindcast, which is basically you start from the initial conditions from 1960, 1965, all those times, and then you have the data, so you can run your forecast model from starting from past initial conditions and verify if it's correct or not. So those we call those hindcasts, and we can run. They will require also thousands of simulated years. So something that requires the whole machine to run one simulated year per day is not going to get us there. So that's the issue. And the second thing we need to worry about is also these models are getting very expensive in terms of carbon and energy. I'm not going to dwell on the results, but we are doing this analysis of what was the energy and carbon cost of the last experiment of comparison between models, which is called CMIP6. And you can see that the numbers are getting us into hundreds of tons of CO2. So this is a project for using these high resolution models of today, which are not quite 1 kilometer, but are in the 3 to 5 kilometer range. And Tim Palmer calls this the Turing test. So if you remember, the Turing test for artificial intelligence is whether you can converse through a window with something and you do not know whether on the other side of the window is a human or a computer. Can you tell just by exchanging messages who you're talking to? And if you cannot tell, Alan Turing said that's an artificial intelligence. So you can make the same argument. I'm showing you several images, and one of them is a satellite image taken from space, and the others are from models. If you cannot tell which one is a model and which one is a satellite, Tim Palmer said that you're passing a Turing test. But the problem, of course, is that you cannot run these models for very long. This diamond experiment, the models run for around 40 days. So we're not anywhere close to running these models for thousands of years. What can you do with the modern computers? So you can do what the problem that they're very, very good at is called deep learning. So you recall that with a few number of words of memory, you want to do as many calculations as possible. So what deep learning does is that given a vector of input quantities and output quantities, you have a data saying that if I given these inputs, I get these outputs. And you try to find the relationship between the inputs and outputs purely numerically. So the normal method you would use is just regression. But you can make it more complicated by introducing a layer of neurons in the middle, so that now the values of the neurons are unknown, but you first compute a regression to this unknown neuron, and then you compute a second regression from the neurons to the output. And now you can see that each of these black lines represents a calculation. So now with the same number of inputs, you've vastly increased the number of computations you're doing. And if you go to deep learning, where you have multiple layers of neurons, you vastly increase the amount of computing. So the modern computers are really, really good at deep learning. They can do huge calculations based on the deep learning algorithms. So which is why we're turning in that direction. So what can ML do? So it tries to take your inputs and outputs and tries to reduce it to a few terms. That's one way of thinking about it, that describe any possible instance of your input. So for example, let's take a human face. It tries to reduce the human face to a certain number of what in ML is called features. And the features describe any possible human face. So now you can take this human face and that human face, and you can compute faces in between. You can compute a face that's 0.3 times this plus 0.7 times that. So any possible human face can be found in this approach. So you think of it as capturing the essence. And so in terms of climate and weather, this is what it means. You have these very high resolution data sets, and you try to reduce it to a few elements that capture the dynamics in that data. That's what we're trying to do with ML. So for example, let's take these same high resolution models of clouds on the globe. And this is a 7.5 kilometer model from a few years ago. And if you want to coarse grain it to this grid, which is the size of the state of Florida, inside that you have many clouds, cloud actions and so forth. So you take the high resolution data, you learn from it what the aggregate behavior of all these clouds looks like. So it's like finding a way to parameterize these clouds using machine learning. So There's been a lot of approaches to doing this. Now it's become one of the most hottest areas in the field, which is trying to find out whether, just from data and high-resolution models, whether you can discover cloud and parameterizations of clouds and turbulence. Remember that whenever you're training, machine learning can only be good as the amount of the training that you do. And remember this problem about the counterfactuals. We have different kinds of uncertainty in our models. The chaotic uncertainty, because it's a chaotic system, it's very sensitive to small changes in initial conditions. We have the scenario uncertainty, which is that we don't know how humans are going to react to the climate crisis. So we may do nothing, we may do something, all these things are possible. And then we don't completely understand the system. We call that structural or epistemic uncertainty. So you have all these kinds of uncertainties. So whenever you're thinking about it in terms of machine learning, you have to remember that the training and to remember that you have to do counterfactuals as well. And models and observations are both sources. I'm not going to dwell on this slide, but we can return to this later. It's not always true that so-called observations, that is reanalysis data sets, may have errors and models may get the errors right. We can discuss that later. But the main thing to think about is that if the climate is warming, in the warm climate, there may be states that you may not see in your training data if you train on present-day climate. So this was a study done from GFDL a few years ago. This is not machine learning, is using methods of statistical downscaling. So what you see here is that the model is trained, if it's trained on present day, this is the histogram of temperatures that it has encountered. So it has seen temperatures that go from this temperature to this range. This is all the temperatures it has seen. But you can train it from a model from the model you can get what you obviously don't have observations, but from a model you can get what the temperature histogram will look like at the end of this century, the 21st century, and you can see that there are all these instances of temperature which is not seen in the historical data. So if you train on this data, you're not going to be able to forecast these temperatures. So this is something to keep in mind if you're doing machine learning. You have to be able to go what's called out of sample. You should be able to generalize to a future which the machine learning has not seen. And similarly, you have to be able to go to the past. I mentioned very briefly the PETM, the Paleocene-Eocene thermal maximum. It's a very interesting time in history because these 4 or 5 points marked here are the observations of temperatures. Again, they're proxy observations. You infer them from other quantities. But you can see near the poles, you have temperatures of 23 degrees and 17 degrees in Antarctica. You can see the continental map is not what you're used to. India is just floating somewhere halfway in between Africa and Asia. But you see the temperatures near the poles were very warm. And this is corroborated by fossil evidence. You have palm trees and you have cold-blooded animals found near the poles. So we know that the warm temperatures existed. The models that we have tried to do this don't do a very good job. They're still looking as though the poles are cool and the equator is warm. So there are some weaknesses, but the paleo data there's too few. Machine learning cannot be done with 5 or 6 data points. But you can use them for what is called as out-of-sample testing. If you come up with a new method based on machine learning, you must be sure that it can. You should ask yourself whether it can do some of these past warm climate well. And let me get into a few details of turbulence and so forth. So learning from turbulent fields. So the turbulence is a problem because it exists at all scales. I'm just going to go through this very quickly. So this is what 2D turbulence looks like. The energy as a function of wavelength has a -3 slope, and then it gets into 3D turbulence where it has a -5/3 slope. And that continues down to molecular scales, essentially down to centimeters. So it's always going to have this slope. So any model you build, whether it's 100 kilometers or 10 kilometers or 1 kilometer, you're going to truncate this. And so you have to learn what is happening in the part of the turbulence that you have not seen. So these are some studies which have tried to learn from turbulent fields. So this is it's not using the planet, but it's using a very idealized domain. But it's a turbulent field of the ocean in a circulating field. And there's some areas where it's highly turbulent, which means you have all these eddies. Some areas it's pretty calm. So what we find from trying to learn these subgrid things is that it depends. You have to be sure that you're seeing all the cases that you want to see. So you have to. Again, these are all the problems, the people who are working with bringing together machine learning and studying turbulence, these are the problems we're struggling with. How do you understand these systems? What data is absolutely needed in order to be able to be sure that you're sampling your turbulent fields correctly. And in the real world, of course, it looks even more complicated. So this is what the Gulf Stream actually looks like. So it's got all these meanders and eddies and all that. So this is a very complicated thing, and this is from a simulation. It's at 2 kilometers of the North Atlantic, but again, we cannot run these simulations for very long, so it's kind of a challenge to learn from them because they're so expensive. What people have been also trying to do is to not just try to find a pattern like I described with deep learning, but actually try to discover the equations. So this is an old paper from 2009, which is called Distilling Free-Form Natural Laws from Experimental Data. So this is a Newton's laws example. This is simply discovering Newton's laws in a Hamiltonian form and Lagrangian form. These are all different ways of writing Newton's laws. They're discovering them just from this data. This one is a double pendulum, and this is just a mass moving back and forth horizontally connected to a spring, which some of you will remember from Physics 101. These are the kinds of problems we used to do. And it's actually finding very reasonable equations directly from data. This has also been applied to fluid fields. So this is Navier-Stokes equations, again, just trained on data. So essentially how it works is that you say that you're trying to solve for, let's take a look at this equation, del omega del t, which is the Navier-Stokes equation. And you say, I don't know what the equation is, but I know that it must be a function of omega, u, and v, and its first derivatives and its second derivatives, and maybe products of those. So here are a bunch of possible terms. You create a library of data and derivatives. And you say, create some function for me that fits the data. And it does a very, very good job. It actually finds the form of the equation which looks like the Navier-Stokes equation. So it's able to find these. In these simple cases where we actually know the equation, it finds an equation. The machine learning is used to actually find an equation which represents your output. So then you can be sure it generalizes to the future because the laws of physics, we hope, are universal. And this is another example of that. I've just, in the interest of time, I'm going to skip over all these examples. This is applied again to the ocean. So I'm going to kind of end here to talk about where climate modeling is going in the machine learning area. So what we've been doing for the last 30, 40 years, Jules Charny, he built his first model in 1950. That model had one vertical layer and it had a grid size of around 50 kilometers. And people said, well, it's a very simple model. And he said, yes, but it's the first step on a ladder. And he said, we're going to climb the ladder of models. We're going to build more and more complicated models. And we have done that. So we have made a very detailed Earth system. We trust it because you can understand individual processes in the model, and you can compare it against other lines of evidence. So that's how trust is built. But you're making the models more and more and more complex. So this leads to what's called the Borges conundrum, which is also a story in Lewis Carroll, where Sylvie and Bruno are going for a walk, and one of them says, I have a map of the countryside that's 1/6 the scale of the countryside, so we'll take it and go for a walk. And the other one says, well, I have a map that's 1-to-1. It's the exact same size as the countryside. So, oh, wow, I'd love to see that. And then one says, well, that's too big. You can't really see it. It's too big. So I leave it at home and I just look at the actual countryside itself. So if you build models that are so big that we can't actually run them very long, then we have a problem. We can't really use it to understand the climate very well. The second question is, supposing you are using pure machine learning, it's not writing down equations for you, but it's just telling you, given these inputs, these are the outputs. Would you trust these? These methods are called model-free methods. Would you trust them? So that's a question to ask ourselves. Machine learning is in the positive phase of a hype cycle. You hear a lot about machine learning almost every day in the news. When you have hype, you have these problems. You have a publication bias, which means that positive results are reported and negative results are not. You have a reproducibility problem. Some results that people are reported, other people are unable to reproduce them. But let's keep in mind it's not all hype. It's actually doing amazing things. And secondly, the hardware is going in that direction. So we do have to contend with machine learning in the future. So the 2 or 3 things I ask people to keep in mind. One is that remember that all your models must be capable of going outside the observational bounds. You must generalize to states you have never seen before because the climate is changing. So I think what we need to do is to be able to use machine learning to build simpler models. which is what I call climbing down Charney's ladder. So if you've climbed up Charney's ladder now for 70 years, we've reached a point where the computing has changed. So we need to maybe come back and start looking at simpler models. And this is, again, it's sort of like the same conundrum Bjerknes faced. He has something that he can write down the equations for, but it's becoming hard to compute. So he said, okay, I'll just do pattern recognition. That's what machine learning is. Think about the energy and carbon cost of computing, because it's getting very expensive. And I think it being the field that is, bringing the warning to the world about climate change, I think we should be conscious of our own carbon costs. And the survey paper is published. I will distribute the slides to anybody who's interested, and all the blue things are links, so you're welcome to click on all the links. So thank you. I'll stop there, Ricky, and turn it back to you.
Great, thank you. We have a couple of questions on our questions document. I can take the presentation back over from you to show the questions for you, and we can go over them.
Oh, yeah, sure.
Okay.
Should I be able to see the questions somewhere?
Okay, we have a link in the chat, or else I just shared my screen. Can you see them?
Yeah, I see them. Yeah, thank you. So it was the print was too small originally, but now I can read it. Okay, question one: do you see machine learning as part of current physical models, or do you see the need for a new type of model trained on data? So there are two things to keep in mind. This is a really good question. If you train it on data, especially if you have two different data sources, let's say, they are not, the data directly is not required to obey conservation laws, for example. So if you take temperature data from one sensor and you take humidity data from another sensor, there's no reason that the two have to be coherent, because they're different instruments. So you need physics in order to make sure that all your observations are coherent with each other. So this has been, well, I know it's been, so this is what we do, for example, for data assimilation, you can think of as going in that direction. You're trying to come up with a trajectory of the weather system, which is, in a least square sense, matches as closely as you can get to all the observations, but not exactly. So you're trying to, so I think it's going to be, as you said, it's going to be a hybrid of the two. There is going to be some machine learning, but you need physics, you need the regular models as well in order to make sense of what the machine learning has learned. I hope that answers the question. The second question is, what parts of physical models are most likely to benefit from machine learning? That's again a good question. So I think the benefit will come initially with the parts that which we're currently doing by parameterization. Parameterization means that you're not actually resolving, you're not actually showing the physics in the model, but you're writing down a theory of what you think the unresolved physics is doing. And then you do that, you measure against field experiments or something, you become confident of your theory, and then you write a representation of that and you embed that in the model. It's highly empirical, and it is done, so that kind of thing, what people have done empirically, anything that has been done empirically, I think machine learning can be a very, very good aid to that. So I think it's going to be the subgrid parameterizations that are going to benefit from machine learning. There are other things, there is a whole sequence of things where I think ML will play a role. The second thing is that the models, even though we run them, we know that they contain errors. And there is often a second phase after the model has been run where you do, you correct the model output by comparing it to data. So you can correct the trajectory. So it's bias correction, for example. So that again has been done highly empirically. It's anything that has been done by people essentially saying, I think it's the bias correction is going to look like this. They look at maps and they come up with some. So machine learning now, because the deep learning now has these very, very deep networks, you can go much further than linear regressions and things like that, which is easier for people to do, because it can find extremely complex relationships between inputs and outputs. So there are many areas in which ML is going to play a role, but I think these two I'll kind of highlight. One is the parameterizations, and the second is post-processing. How do you distinguish between ML and artificial intelligence? I personally don't use the word artificial intelligence if I can help it, because I think that's a misnomer. I think it's a marketing term. Artificial intelligence is supposed to be capable of reasoning. So I'm trying to be very, very clear here. Machine learning is just building complex statistical relationships. So it is taking statistical techniques which are already known to the community. So nothing was invented in machine learning. They use new terminology for a lot of things, but most of the tools of machine learning have been in the statistical community for decades or 100 years even. What is new is that now you can apply it to very large data sets and you can use very large computers. So you can do it on a scale you could not do it before. So if it were me, I would not use the word AI at all. I would only talk about ML. Even the AI that is dealing with languages and all that, it is still only doing ML. It is basically taking elements of a language and is converting them into a vector, which is just like in the deep learning graph that I showed you. And it is trying to convert the input to the output vector mathematically, and then the output vector is reconverted back into language. That's how NLP, natural language processing, works. So you can do amazing stuff. So this GPT-3, the new NLP machines that coming out of Google DeepMind and all that, they can translate in real time as you're speaking. They can do fantastic things, but it's not the original challenge of AI. It's not what used to be called strong AI, where there is a sense that the AI actually knows what it's talking about. It doesn't. It's just mapping.
So I don't know if a new question, this is Ricky, the new question is being written now or just a place for it. But I do, while that question is being written, if you were thinking about computational strategies for a large model, large organization, would you be investing in refactoring for GPUs, or would you be thinking of taking on sort of a more strategic approach to maybe transformation of models?
Yeah, thanks, Ricky. So that's a good question. So I'll make my position clear. So I have not been ever convinced, and I'm still not convinced that GPUs are going to solve differential equations efficiently. So and they will give you some acceleration, but remember that the Dennard scaling, no matter what you do, that's a physical problem. It has ended. Arithmetic is not going to get faster. The computers are getting bigger, but they're not getting faster. I think that's one way to think about it. So we should not be thinking of them as faster computers. On the other hand, if you're going to be doing a system that's a hybrid ML plus physics-based model, I can think of very, very good ways. There's the infrastructure, the software needs to be written, but there are definitely good ways of what is called inline learning. A lot of learning that's done today is done by you look at observations, or you run a model at very high resolution, you save the output, and then you try to learn from it after the output has been written. But because of the volumes involved, we cannot save as much data as we would like. So, but imagine you were doing this learning in line as the model is running. Then the model has access, the machine learning agent has access to the full model state. It knows all the variables at every instant in time. And I can definitely think strategically, Ricky, of designing a system where as the model state advances, it keeps sharing its data to the GPU, where a machine learning agent is trying to build a reduced dimensional representation of the same data. And it keeps going on. There are many new techniques in machine learning of processing time series, such as recurrent neural networks. But they're not new, but they're strong techniques. So they can as new data keeps arriving, they can keep refining their learning. And I would think that's one of the best uses I can think of a hybrid CPU-GPU machine, is to have the models running on the CPU and a learning agent always accompanying it on the GPU. one of the points I want to make about the carbon cost and energy cost of modeling is that these models are so expensive in energy, it's a shame to throw away even one bit of data if you can help it. So if we can come up with a way where something can really examine the model state at every time step, I think there's a lot of information there that today we're throwing away. I think GPU-based machine learning would be wonderful for that. Please describe what the CMIP6 offers over Manabe and Charney and what is still the same, and what CMIP6 simulations are reliable enough to use for ML inputs. Let's remember that Manabe and Charney they basically left out a lot of physics because they were also limited by the computers of their time. And Suki has been talking to us a lot lately after his Nobel Prize. So I've had a few chances to chat with him, and he's given many public talks about what we should do with models. And he has been saying again and again that don't make your model so complicated that you cannot understand the model. So you build a model so that you can actually understand what, once the result is coming out of the model, you kind of have a sense of why it is doing what it does. And GFDL, because of its long history, we have had a long history of people who actually have studied models, and they actually can sometimes uncannily tell you what the model is, how a certain model is going to behave. So what can CMIP6 do that those models cannot do? It can, for example, currently there is a lot of the CMIP6 models have gone into this thing which has made them very complex. What has made them very complex is they're trying to see what the relationships between aerosols and clouds, and trying to actually represent that correctly. So you release aerosols into the atmosphere, and that changes the properties of the clouds. And what that does is very hard to see. And there's different kinds of clouds. There's boundary layer clouds, and there's deep clouds as well. And all of these have a huge effect on the climate. So we have actually, on a physical level, the models of today are much more accurate than the models of Manabe and Charney, because they have these details which they left out. They made large approximations, and they also had to put in various fudge factors in order to make their models conserve energy and so forth. So I'm not criticizing the models. I mean, they were wonderful models, and we still do learn a lot from them. And as I have pointed out, we have the uncertainty bounds on ECS have not changed since Charney's time. With the complexity, you also get the problem that once you put in this complex physics, they interact with other parts of complex physics, and then we don't know how the whole system behaves very well. So we still struggle to understand what the models are doing, even though the physics we believe on a process-by-process level is more accurate. And what CMIP6 simulations are reliable enough to use for ML inputs? Many of them are. So there have been some very, very good ML papers that I can talk about. So one, for example, is doing the forecasting of El Nino. It's a paper from 2019 out of Korea. And what they did was they initially trained on, so they use a method which is called transfer learning. So you do your basic learning on a very large data set, and then you correct that or refine that using a smaller data set. So they took the CMIP5, so this is 2019, before the CMIP6 data came out. And they learned the kind of long-term behavior of ENSU across all the models. So the models all have errors, we know that. We hope that the errors are independent of each other. So if you train for over a lot of them, you will cancel out all the errors, and you will learn what is correct in all the models. And then later you use reanalysis to refine it towards later stage data. And these models, the predictions from these models are very, very good. So ML is able to learn from these models already, but I think it's useful to learn from large ensembles of models. So you're kind of making sure that you're not adopting the biases from any model, because we all know if you've been following the use of ML in society, if in the use of in the areas of racial justice, for example, ML that is trained on data that has racial bias will reproduce, the gender bias for that matter, will reproduce those biases. Same is true of models. But if you average over a lot of models, the CMIP6 ensemble can be useful for ML.
Great, thank you so much. It was a really great presentation, but we are at the top of the hour, and so we will end for today. Thank you everyone for attending.
Thank you. Thanks everybody for coming.
Thank you.